Welcome to this highly technical deep dive. Today, we're basically acting as your co-presenters, and our mission is to deconstruct the MEKA precision conveyor engineering document.
Right, and we're delivering this like a slide deck for you, really getting into the rigorous math and the physical laws governing massive material transport.
Yeah, because when you are moving a literal mountain of rock or coal, you can't just rely on guesswork. I mean, if your math is off by even a fraction, you don't just get a minor bottleneck.
No, you snap a steel-reinforced belt.
Yeah.
It's a catastrophic system failure.
Exactly. Okay, let's unpack this. On this slide, we see deliverable capacity actually relies on 5 interacting inputs, and miscalculating just one chokes the loading point or causes tension failure at the drive drum.
What's really fascinating here is that core interaction. I mean, it's not just about speed, right? It is about balancing the geometry, the kinematics, and the material properties all at once.
Moving to the next slide, we look at volumetric throughput. And, my instinct is to think of it kind of like a highway. Doubling the belt width more than triples the throughput because it grows with the square of the width.
Yeah, the math on that is wild.
Right. But doubling the speed is strictly linear. So from a pure engineering standpoint, isn't it always better to just go wider rather than faster?
Well, generally, yes. Widening is consistently more cost-effective over its life cycle. But there is a crucial particle size constraint you have to consider.
Oh, what kind of constraint?
So if your mix is, say, 80% fines, like gravel, dust, or sand, it actually acts as a cushion.
Oh, like sandbags.
Spot on, like little sandbags protecting the hardware.
Yeah.
That cushion allows for significantly larger lump sizes to ride the belt without causing point load damage to the rollers underneath.
Okay, that makes sense. Moving to the next slide, we break down total force into F1 through F4. So we have empty belt friction, horizontal transport, gravity lift, and skirt friction.
And if we connect this to the bigger picture, F2, which is the material transport force, actually scales inversely with belt speed.
Wait, really? Inversely? That feels counterintuitive.
I know, it trips a lot of people up. If the belt is faster, you'd think it needs more force. But a faster belt carries a thinner, lighter layer of material for the exact same tonnage.
Oh, I see.
Yeah, so you're moving less mass per meter of belt at any given second. Less mass pressing down means less horizontal drag.
Ah, okay, when you visualize the layer getting thinner, that clicks. So on this slide, we convert these forces into power. And the crucial engineering rule here is size up, always step up to the next standard motor frame to absorb feed surges.
You absolutely have to.
Yeah.
And this brings us to the Eytelwein Capstan equation, which is critical to prevent slip at the drive drum.
Right, it calculates that grip to slip ratio, basically.
Exactly. But I need to issue an iterative loop warning here.
Uh-oh.
Yeah. Let's say you specify heavy rubber covers to deal with abrasive material. Well, that increases the belt's overall weight, right?
Right, which means you must loop back and recalculate the initial F1 empty belt resistance.
Yes, it's a closed punishing loop. Changing one variable like a heavier belt forces you to recalculate friction, which changes your force, which might mean a larger motor. You iterate until the math completely settles.
Wow. So what does this all mean for you, the listener? Designing a conveyor isn't a straight line. It's an iterative loop where precision at the loading point dictates power at the drive drum.
It's absolute mathematical precision or total system failure. No in between.
Exactly. Which leaves us with a final provocative thought to mull over. Since miscalculations in these static engineering formulas cause such catastrophic mechanical failures, how long until heavy industry completely abandons manual variables?
That's a great question.
Right. Imagine a future of AI-driven self-tensioning conveyors that dynamically adjust belt speeds and motor outputs in real time, just instantly responding to every feed surge.
It would completely eliminate the human error from the iterative loop.
It really would. Well, that's all for this deep dive. Thanks for joining us.